Hi. Um, in this section of Chapter 3, we are going to be talking about the arrangement of the electrons in an atom. We'll talk about how they're placed in these orbitals and how they dictate chemistry, and then I'll show you how to determine the electron configuration. The electron configuration basically tells you the address of each electron in a particular atom. So this is 3.03. EMR stands for electromagnetic radiation, and we're looking at the hydrogen atom because the hydrogen atom is the simplest atom, and it gives us a model to figure out how the electron plays a major role in the properties of an atom. So far we've talked about the development of the atomic theory and how Rutherford gave us a dense nuclear model of the atom. We haven't talked about Bohr yet, and so this is the section in which Bohr is going to give us the planetary model of the atom, and Schrödinger is going to tell us that the electron can be described as a wave. So the important part about this particular section is that we're now using a tool to probe the parts of the atom, and the tool that we're going to be using is light. So what exactly are the components of light, and how does light give us an idea of how electrons are arranged in the atom, and what is the relationship between light and an atom? An atom can actually emit light or absorb light, and the question is, what is that relationship? And then finally, how does light give us clues about the structure? How do we use it as a tool? And the last question, which will be towards the end of this particular section, is how do we know what the composition of the sun is? How do we know it's mostly helium and hydrogen? We haven't been to the sun, and we haven't sampled the chemicals on the sun, so the question is, how do we know it's mostly helium? And how do we know that the atmosphere on Jupiter is methane? What clues provide that information? How do we know that there are waters in the moons of Jupiter? What information provides that? And so this particular chapter will give you that information, will give you the knowledge as to how we're able to determine the chemical compositions of distant stars even though we haven't been there. So let's take a look at light, which is also called electromagnetic radiation. And the electro and magnetic portion of light, there's two components of light basically, and these components are electrical and magnetic. And so these are shown here. Light's actually a wave. It's a form of energy. And so if you look at this diagram right here, you can see that it has, just illustrate this, two components, and those components are 90 degrees from each other. You see this wave right here, okay, and you see this wave right here. And those are the electrical and magnetic portion of light. They're what we call orthogonal. Orthogonal just means that they're 90 degrees to each other. So any type of radiation, electromagnetic radiation, whether you're talking about light or heat, or microwaves, or gamma rays, or X-rays, or radio wave, have both of these components. The difference between, say, a radio wave and a microwave, or even infrared, which is nothing more than heat, is the wavelength of light. Here you have an illustration showing red light and blue light. What makes them different? What makes these radiation different? The wavelength. You notice that the wavelength of this particular wave is longer than this right here. That makes red light a lower energy radiation than blue light. The longer here, the shorter the wavelength, the higher the frequency, the higher the energy. So that's the illustration that we have for light. So if you take light, just plain white light, if you have a flashlight for example, and you radiate it through a prism, what you'll find out is that white light is actually the superposition or the overlapping of red, green, yellow, blue, indigo, and violet, the colors of the rainbow. A prism separates the wavelength of light because it takes these wavelength of light that white light is composed of and separates them. So what you have here is that visible light is actually the combinations of the color of the rainbow. And you notice that in this particular illustration, what we have is red light. It has a wavelength of 700 nanometers. What does that mean? It means that from crest to crest, when you're measuring a wave, from here to here, for red light, that's 700 nanometers. Remember what nanometers is. It's a unit of measurement for length in the metric system. On the other hand, violet light, if you measure the wavelength from crest to crest, from here to here, what we have is 400 nanometers. It's much shorter, and so the wavelength of light is shorter, the frequency is higher, and the energy is also higher. So, if we take a look at the electromagnetic radiation series, what we have here is that we have energy going from lowest to highest, and that the lowest energy that generally electromagnetic radiation that we have is radio waves, TV waves. These have wavelength in the order of about 10 to maybe 1 meter. That's the size of these wavelengths of light. As the wavelength of light gets smaller, in the orders of say centimeters, then we get to microwaves. When you get to micrometers and millimeters, you get to infrared. When you get over to 10 to the minus 9 nanometers, then what you have is visible light. Even shorter than that, you get ultraviolet light. Shorter than that, X-rays and gamma rays. So all these you know from your everyday experience: radio wave, infrared, ultraviolet, but it's a series of energy that is under the umbrella of electromagnetic radiation. And if we blow up visible light right here, what you see is that we have the lowest energy at 700 nanometers, red light, and the highest energy, 380 nanometers, ultraviolet or violet. So, back in the turn of the 19th century, 1890, 1900, scientists were trying to probe the atom, trying to get a better idea of what the parts of the atoms were, and they were using light to kind of give an idea of what parts of the atom, what were the parts of the atom. And so Planck and Einstein, Maxwell Planck, gave us the equation that the energy of light equals h nu, where h right here is a constant. It's called Planck's constant, and nu right here is the frequency of light. That is, how fast does, say, the trough of a light pass a certain point in space. So Planck gave us this equation. The energy of a light is equal to h nu. In fact, you need to put a variable in front of that, because he also told us that light is quantized, energy is quantized. So what we need to do is actually, if you've taken physics, we actually have to multiply that by n, where n represents an integer. Okay, so that basically is Planck's equation. You guys know about Einstein, brilliant scientist. He gave us the theory of relativity and special relativity. He also said that energy and matter are related by E equals mc squared. Well, 1/2 mc squared. What these two equations, if you combine it, you take Planck's constant and Einstein's equation and you combine it, what you have is that you see that light, wavelength of light, has mass. So it's pretty phenomenal in that we're trying to think of electromagnetic radiation, and it's got a certain mass. We say it has momentum. Now, why is this important? Because that at that time, what scientists were doing was trying to use light to probe the atom, and as they were using light to probe the atom, they noticed that light, electromagnetic radiation, had peculiar properties. Sometimes it behaved like a particle, sometimes it behaved as a wave. And so Planck actually said that light can be described as a photon. A photon is nothing more than a particle wave. And so this is how you can depict different photons. You see this right here, how the wavelength of these right here are shorter than the wavelength of this. So this photon might have a higher energy than this photon. But here you can see how this illustration right here gives you a particle wave duality pictorial. And so that was what was proposed by Planck, and Einstein certainly supported that. Now, another scientist by 1932, in fact it was just a graduate student, he said that, well, if light can have particle-like properties, can particles or matter have wave-like properties? And so that was the whole premise of Louis de Broglie PhD thesis. And guess what? He is the only graduate student, PhD candidate, that has ever won a Nobel Prize, because he did prove that you can take any matter, you and I actually, and calculate the wavelength of we can get some sort of wavelength property. We can calculate our wavelength. Anyway, that's beyond us, but he did say that particles have wave-like property. Now, why is this important? Because it sets up the idea that electrons, which we always think of as a particle, may sometimes behave like a wave. And this is the basis of quantum mechanics. Okay, now quantum mechanics is a theory that doesn't apply in our world. In fact, it doesn't make any sense. It's used to explain the atomic scale, because in the atomic scale, our world, the laws in our world, what we see around us, doesn't apply there. At quantum mechanics, the atomic scale, you need different set of laws, you need different set of explanation, and that's quantum mechanics. So let's take a step back, and now we have some idea about light, its properties, and even matter and some of its property. But if we go back to electromagnetic radiation and we look at visible light, we can see here in this particular diagram that visible light is part of the electromagnetic radiation. It goes from red all the way to violet, Roy, red, orange, yellow, green, indigo, violet, Roy G, Biv. That's the way I learned it in 7th grade, the different colors of the rainbow. And here you can see that if you take white light and hit it through a slit, so you get one type of light going in one direction, and you put it through a prism, you get different colors of the rainbow. But if you now take, say, a chemical, an element, and you excite that particular element, okay, with radiation. You give it enough energy so that you excite it. You kind of like spark it up, or you give it an electrical discharge. Then that atom, that element, will also radiate light. But it doesn't radiate light in the visible spectrum. In fact, it radiates light with a specific frequency. This is called the atomic line spectrum phenomena that was plaguing scientists back in the early 1900s. They didn't understand why certain elements gave a particular set of wavelength of light. In fact, if you take a look at hydrogen, if you put hydrogen here and excite it, these are the wavelength of light. No other colors were emitted. These were the colors that were emitted in the visible spectrum, by the way. There's actually other colors in the ultraviolet and other colors in the infrared, but we can't see it, so it's not shown here. This is sodium, yellow, orange color. This is helium, this is neon, and this is mercury. And scientists were sort of perplexed as to what were the origins of these atomic line spectrum, these specific wavelength of light that were coming out of the atom. It must have given clues as to how the atom is built. And let's just do a discussion on the hydrogen atom, because if we keep our discussion simple, in which we have one proton and one electron, maybe we can make sense as to why each element has this unique atomic line signature, and how we can tell just by exciting a specific element or a specific molecule and looking at the atomic lines that come out, how to identify them. Anyway, if we take a look at the hydrogen atom and we get some hydrogen gas and we hit it with some sort of high energy, H nu, remember, is high energy light, then we can cause that hydrogen molecules represented by two hydrogen atoms bonded together, so we write it as H2, okay, H2, like that. But what happens to the hydrogen molecule right here is that it sort of splits out, and the electrons in each of those hydrogen atoms are excited, because the way an atom absorbs energy is by taking the electrons and promoting it to what we call a higher energy state. So that's what we represent here as a star. And then once that particular atom is excited, as the electron go back to the ground state, that is, it goes back to where it came from, light is emitted. And so for the hydrogen atom, the light that we see are over here at 434 nanometers, 480 something nanometers, and out here at 670 nanometers. We see somewhere light in the order of red, turquoise, and violet. And the question is, well, what gave rise to this specific light? And the answer is based on how the electrons are arranged in the atom. So Bohr looked at this and he said that, well, I think I can explain this atomic line spectrum. I think I can explain, or I can propose a theory. Again, it's a theory. Remember what a theory is. It's an explanation that makes sense, that explains observation. So his explanation is based on the planetary model. He says that an atom has its nucleus in the center, just like our sun, and then it has its electrons orbiting in a fixed orbit around the sun, with certain distance around that sun. So with hydrogen, with just one proton and one electron, okay, one electron, you have just one electron orbiting that nucleus. And what happens is that this electron is going to be orbiting at a certain distance from the nucleus until you give it some sort of energy. So That was Bohr's planetary model of the atoms. He said that electrons follow circular orbit around the nucleus. Electrons can only have a certain size orbit, and that the electrons allowed to a higher orbit, they can go to a higher energy. Okay, these electrons over here can go to a higher energy orbit if it receives certain energy of either light or some sort of other energy to pump them up. It's like taking you from, say, let's imagine you sit in front of a hotel, let's say 100-floor hotel. Well, how do you get that up to the 50th floor? Well, you need energy. You need energy by, say, like an elevator. The elevator will require energy to take you from the ground floor to the 50th floor. Now, when you are at the 50th floor, you're what we call the excited state. So the same with an electron. The electron is in the ground floor, first shell. Okay, we call it principal quantum number 1, first orb energy level. And if it wants to go to the 50th orbit, or the 3rd orbit, or the 10th orbit, it needs to receive some energy from the outside. Once it's up there in the 3rd or the 4th orbit, then it needs to get back down to the ground floor because it's not stable in the higher energy orbit. It needs to relax back down. And that's what we call relaxation. And as it relaxes back down, that energy that it absorbed has to be released. And when it's released, that's the energy that you see for the atom. So that's basically what Bohr proposed. Now this is the atomic line spectrum for the hydrogen atom. Here you can see the specific wavelength. There's one over here at about 410, there's another about 430, there's another at about maybe 587, and another out here at maybe 655. Where did this come from? Now I realize this is a little bit complicated. This model right here is a little bit complicated. So just imagine we have a hydrogen atom with 1 proton right here. Also imagine that we have a hydrogen atom with 1 electron. Let's say it's right here. Okay? Now, what will happen is that for one, if we follow just one hydrogen atom, and we excite this electron with some sort of radiation, then this electron is going to go from, say, this energy level. So let's say it jumps up to the 3rd energy level right here. Okay, so it goes from the 1st energy level and it jumps up to the 3rd because it absorbs a specific energy of say radiation that makes it go to the 3rd. Maybe a higher energy will make it go to the 6th, maybe a higher energy will make it go to the 8th. But for this one hydrogen atom, it's going to the 3rd. Now this electron needs to go back to the ground state, n equals 1. What are the path for this electrons to go back home to the ground state? Well, it has a path of the following. It can go from the 3rd level to the 2nd level, okay, and that represent one type of radiation. The energy of the radiation is proportional to that length right there, and then once the electron is in the 2nd, it'll go down to the 1st, and that's 2 types of radiation. So that's 2 different frequencies of light, or 2 wavelengths of light. Okay, maybe the electron, another atom, has its electron promoted to the 3rd shell. Maybe that electron doesn't take the path of 3 to 2 and 2 to 1. It goes from 3 to 1 directly. Well, then that's just one wavelength. It's going to be a higher energy wavelength because that transition is longer, representing higher energy, shorter wavelength. Okay? But it still needs to go home. Now imagine if you have millions and millions of hydrogen atoms. Well, some of the electrons are going to go to the 1st or the 2nd shell. Some of the electrons are going to go to the 5th or 6th or 8th or whatever. But each of those electrons in these millions of hydrogen atoms are eventually going to relax back down to the ground state. Now what does that mean? It means that when the electron starts cascading down, then they're going to release a specific energy. Imagine like you have 100 people in the ground floor of a hotel. It's 100 stories, okay? And there's many elevators. And once this, people dissipate, some goes to the first, some goes to the 10th, some goes to the 100, okay? And each one of those person, let's say, represent a different hydrogen atom. Well, how do each of those individual come back down to the ground floor? Well, some of them who are in the 100th floor will take the elevator from 100 to the ground floor. Some will take it to the 99, then 98, then 97, then 96. But each time they make that jump, that's a specific energy that they are releasing. And so that's what this particular diagram illustrates, is that when the electron, let's look at the Lyman series, are promoted to higher energy state, and the electrons that are in the high energy state make a transition from where they are to the ground state, that's called Lyman, and that's in the visible spectrum. The final state for these electrons is to the ground state. Now, let's say that a series of atoms are also excited to a higher energy state, but now when they try to go back to the ground state, they go to the second energy level ultimately. Well, that's called the Balmer series. Okay, that's called the Balmer series. Excuse me. Eventually, all of these electrons right here are going to go from n equals 2 to n equals 1. Okay, that's what they need to do to get back home. But these transitions, called the Balmer series, when the final state of the electron is 2. When the final state of the electron is 3, it's called the Paschen. And here you can see the different energy for each of these transitions. These are going to be the longest because they have the longest journey. So they're going to have the highest energy. This will have the next most, because if you look at these transitions, they tend to be in the middle of the road. So that's where the Balmer series is. These transitions are going to be the shortest, because if you notice, the further you go out in an atom, the closer these energy levels become. So that's going to be the lowest energy. The lowest energy is going to be out here in the infrared. So I hope you have a better understanding of how the atomic line spectrum arises. It arises because the electrons need to relax back down to the ground state, and they take different paths. And each path represents a specific wavelength of light, a specific color. And so that's basically what the atomic line spectrum does. And for different atoms, guess what? Because the energy spacing between each orbital was different, the transition back down to the ground state is going to be unique for each atom. And so that's why each atom, each molecule, as a matter of fact, has a unique atomic line spectrum fingerprint. And now we know how we can tell that the sun is mostly helium, because when we look at the radiation coming from the sun, the light that's coming from the sun, we can separate those wavelengths of light that matches the helium atom. Okay, so that was basically how the atomic line spectrum was explained by Bohr and some other scientists. But the thing is that the hydrogen atom is easy to explain when you electrons are easy to explain. You can calculate their energy when there's one electron and in an atom. But once you get more than one, this model sort of becomes complicated. The energies of these electrons are difficult to calculate, and so they had to go to a different type of theory to try and explain the nature of electron. And that theory is quantum mechanics. And quantum mechanics simply tells you that these electrons are housed in these different orbitals. This is the first shell, this is the second shell, this is the third shell, the fourth shell, fifth, sixth. Remember this diagram right here? right here where you have concentric spheres, well, that's what these are right here. And if we look at the energies of all these orbitals, it can be represented by that, where the first shell, n equals 1, we call it n because that's a quantum number. It's called the principal quantum number. That's the first. This would be the second. This would be the third, the fourth, and there's infinite amount of orbitals actually for any particular atom. But within each orbital, you've got something called suborbitals. Okay, suborbitals are the type of behavior, the type of probability of finding a particular electron. So when you look at n equals 1, the principal, the first shell, it's a small orbital. You can only fit 2 electrons here. Okay, and that's called the s orbital. All of these are s orbital right here. Okay, so for the first shell, you only have an s orbital. The second orbital right here, okay, it's bigger, so you can accommodate more than two electrons in here. And so it's made out of s right here, s right here, and p. But for the p, there are 3 types of suborbital. And if you look at these right here, there are 1, 2, 3, 4 what we call boxes or rooms where electrons can be housed. For any one of these boxes or orbitals, we can put 2 electrons, and I'm representing electrons as arrows. Okay, the electrons must have different spin. We call it spin. And so if you look at the second shell, we can fit 2 here, but because there are 3 here, we can fit a total of 6. Okay, we can fit a total of 6. So 6 plus 2 is 8. We can put 8 electrons in the first shell. Second shell, we can put 2 electrons in the first shell. Let's look at the third shell. We've got the s, we've got the p, and we have a d. And we can put 10 here, we can put 6 here, and we can put 2 here. That's a total of 18. 18. And if you look at the fourth shell, we've got an s, a p, a d, and an f. There are 7 f suborbital, total of 14. There are 5 d orbitals, total of 10. There are 3 p orbitals, total of 6, and there are only 1 type of s orbital, total of 2. So you can see that in the fourth shell right here, we can put a total of 14 plus 10 is 24, plus 6 is 30, 32 electrons. 32 electrons can fit in here. So now you can see how complicated an atom is. The light atoms with very small protons have very few electrons. But as you add more protons, you're going to have the same number of electrons if it's a neutral atom, and it can get pretty complicated. Anyway, the electrons are going to be filling these suborbitals, and these electrons can be promoted to these empty, higher energy orbital. Each of these electrons in these suborbitals have an address. N tells you the level, first, second, third, fourth, fifth. L tells you the orbitals, S, a P, a D, or an F. M sub L, also called the magnetic, angular momentum quantum number, tells you the different type of suborbitals. For P there's 3. For D there's 5. For F there's 7. And then the M sub S tells you the magnetic spin quantum number, and that tells you whether the electrons are spinning clockwise or counterclockwise, and we depict that by either right side up arrow or upside down arrow. Yes, it's a lot, it's very complicated, and if you take general chemistry, you're going to learn this in and out. But here I'm just kind of giving you a glimpse of what quantum mechanics is and how we explain the electrons of an atom using some of the quantum mechanics results. And guess what? This is Schrodinger, and he's the guy that proposed that electrons is best described as a wave. In fact, he published his work in 1926, and he said that that the electron, it's so complicated that he gave a theoretical explanation of the electrons in an atom and said that these things can be visualized as a wave, and it was the second theory that was proposed about the electrons. Heisenberg and proposed something called the Heisenberg uncertainty principle, and it was based on mathematic matrix, and the physicians at that time were at war as to which theory to believe. Schrodinger was much easier to visualize, but Heisenberg was much easier to see in terms of the mathematical relationship. Schrodinger did some calculation, and he said, no need to argue. These two theories are actually the same. They just present it in a different form. So that was Schrodinger. So you have an idea of how we were able to at least get an idea, how we're able to probe how the electrons are housed in an atom. And if you know fireworks, then you know that when it explodes, it emits these different colors of light. And remember, these different colors of light are basically the line spectrum of the unique element that makes up that firework. And so, if you go to this website, if you have time, go to this website, www.pbs.org, wgbh/nova/fireworks, and you'll see this site. Let me show you this site, and kind of show you what I mean by this. Okay, you're gonna have to bear with me because my mouse here is a little bit slow in its response, so I have no control. Okay. Okay. So if you go over here to the Nova Fireworks, this is it. And for some reason QuickTime doesn't work here, but if you go to this site, let's just go to home real quick, what you'll see is the following. Let's see. So this gives you an idea of the anatomy of fireworks, but this is the interesting site in terms of Name That Shell, because if you go to this site right here, then you can look at the different patterns that you see during fireworks, and you now know the name. Like this right here is called a coconut. Okay, this is called a peony. This is a Roman candle, a poinsettia, a ring. And so if you just go to this website and you can get the QuickTime plug-in to work, you can actually see the different types of firework and see what it looks like. And next time you're in a fireworks show, you can name them. So that's that website, and then we're almost done for this particular part. So this is the summary of what we just talked about. We talked about light and how it travels through space. It actually has a constant speed in a vacuum, but if it's not in a vacuum, you can vary its speed. the wavelength of light is measured from crest to crest, or trough to trough. That's the bottom of the wave. And the cycles is how many cycles passes a certain point is called the frequency. Remember that the shorter the wavelength, okay, the shorter the wavelength, the higher the frequency. The higher the frequency, the higher the energy. And this is related by this equation right here. The equation is E following. We can say that E equals H C over lambda, where lambda is the wavelength of light. So you can see this inverse relationship between the wavelength of light and energy. And E is also equal to H nu. Okay? H is Planck's constant. It's a number. You can look it up. I think it's 6.64 times 10 to the minus 34 joules per second. C is the speed of light. Lambda is the wavelength of light, and so you can see that there's an inverse relationship. The shorter the wavelength, the smaller the wavelength, the higher the energy. The smaller the wavelength, the higher the frequency. The higher the frequency, the higher the energy. So that's something that you should remember. And then Max Planck told us that energy is quantized. Niels Bohr gave us the idea that electrons orbit the nucleus in some sort of a planetary model, and he was able to explain the atomic line signature of each atom. And then the electrons can't be really thought of as a particle. Some of its properties are very difficult to explain if they were a particle. So Schrodinger said that you could, and Heisenberg said that the best way to explain an electron is that sometimes it's a particle, sometimes it's a wave, and we can treat it as a wave if we want to calculate its energy. And so the main thing that you saw here was that each atom has a unique atomic line signature because the energy levels of each atoms are different, and so that gives rise to different colors. And so you can see it from this movie right here.
In this experiment, we are going to look at the characteristic colors given to flames by alkali metal compounds. The first flame is the red flame caused by lithium. Lithium chloride on a platinum wire gives a red flame when inserted into a Bunsen burner flame. Next, sodium chloride. Sodium chloride is placed on the platinum wire. It gives a characteristic yellow color when placed in the Bunsen flame. These colors can be used to qualitatively identify the presence of the metals. A yellow flame always indicates the presence of sodium. Finally, potassium chloride. Potassium chloride on platinum wire is placed in the flame, and it gives the characteristic lilac color. All these colors arise because the alkali metal atoms are raised to excited states by the temperature of the flame, and then return to the ground state, emitting light of a characteristic frequency.
So that sort of explains why we have unique colors for different compounds as well, and why fireworks we can generate different colors based on fireworks. It's the chemicals that they put into these fireworks. And so that ends this particular section.